Why does Kruskal's algorithm always produce minimum spanning tree? In the last two lectures, we learned about Kruskal's algorithm, and there we had seen that Kruskal's algorithm always produces minimum spanning tree of a graph. Then the question is, how can you say that this algorithm's output is always a minimum spanning tree? That is, you know the algorithm, you know the steps that are to be followed, but what is the proof for the fact that the output of this algorithm is always a minimum spanning tree? This is what we are going to prove in this lecture. We'll prove that whenever you apply Kruskal's algorithm on a graph, it will always give you the minimum spanning tree. What we'll do is, we'll split this into two parts. In the first part, we'll prove that whatever is the output of Kruskal's algorithm, that is a spanning tree. It is not just a tree, but the spanning tree itself. And in the second part, keeping the first point in mind, that is, considering that it is always a spanning tree, we'll prove that it is specifically the minimum spanning tree itself and not any random spanning tree. So this is what we are going to do. In the first step, we'll prove that it is a spanning tree, and then keeping this point in mind, we'll prove that it is not any random spanning tree, but it is specifically the minimum spanning tree itself. So let us start with this proof. Initially, we have to prove that it is a spanning tree. Whatever is the output of Kruskal's algorithm, that is a spanning tree. How can you prove that? Let us go through the steps that are followed in Kruskal's algorithm. First thing is, you always start Kruskal's algorithm with an empty set, or you can say an empty MST. Thereafter, you are going to build this MST by repeatedly adding the smallest edge that is possible. That is, whichever is the smallest edge among the remaining edges, you will pick that edge, and then you will check whether there is a cycle, because this is important. You will check whether there is a cycle, and if there is no cycle, then you will add this particular edge to the graph, that is edge to the MST. This is what you do in Kruskal's algorithm. And then when do you stop this algorithm? You will stop this whenever you are done with v minus 1 edges. This is what you generally do. And at this point, your graph will be connected, and at this point you can know it is a spanning tree. The next question is, if you know these many points, how can you say this is a spanning tree? Let us look into the definition of spanning tree. What is a spanning tree? A spanning tree is a subgraph of a graph G which connects all the vertices of that graph with the minimum possible number of edges. This is what is a spanning tree. Here, when I say minimum possible number of edges, this is a specific number. That is, whenever you have a graph which is having v vertices, the minimum possible number of edges using which you can connect all the v vertices is always v minus 1. So whenever you have a spanning tree, that spanning tree must be having v minus 1 edges. So the next point is, whenever you find a graph that is a subgraph of a graph which is having v minus 1 edges and it connects all the vertices, then it has to be a spanning tree. Why is it? Because you know that there are v minus 1 edges, and you know that these edges are connecting all the vertices of a graph. So if it is connecting all the vertices and it doesn't have a cycle, that means it has to be a spanning tree. So because you know that Kruskal's algorithm will form v minus 1 edges, and you know that there is no cycle possible in Kruskal's algorithm, it is confirmed that whatever is the structure that you get at the end of Kruskal's algorithm, That is a spanning tree itself. So at this point, you know that whatever you built from Kruskal's algorithm, that is a spanning tree. The next question, the most important question is, how can you say that this is a minimum spanning tree? See, saying that it is a spanning tree, it is comparatively easier. You just have to compare the properties and you can say this is a spanning tree. But proving that it is a minimum spanning tree, that is what we have to do. So what we'll do is, in order to prove that this is a minimum spanning tree itself, we'll do a proof by contradiction. So in order to do this proof, let us assume that whatever is the output of Kruskal's algorithm, that is a spanning tree but not a minimum spanning tree. This is the assumption that we are making. We know that we want to prove that it is a minimum spanning tree, but in order to do that proof, we are going to do proof by contradiction, and for that purpose, we are assuming that whatever is the output of Kruskal's algorithm, that is just a spanning tree and not a minimum spanning tree. So I'll call this tree as T. So T is the tree that I obtained by applying Kruskal's algorithm. And what did we assume? We assumed that this particular tree T is a spanning tree but not a minimum spanning tree. We already proved that whatever is the output of Kruskal's algorithm, that is a spanning tree. So this is for sure. But we are assuming that it is not a minimum spanning tree. If this is the case, then there must exist a tree called T star, which is the actual spanning tree, the true minimum spanning tree of the graph. If T is not the spanning tree, then there should be some other tree which is called T star, which is the actual spanning tree, actual minimum spanning tree of this graph. And let us say this T star, that is the true minimum spanning tree which is having maximum number of edges in common with T. This is our assumption. So we are assuming that T star is the minimum spanning tree which is having maximum number of edges in common with T. So T is the tree that we obtained from Kruskal's algorithm. So this much is the assumption that we are making. If this is our assumption, then since T star and T are different trees, there must be at least one edge which is present in T star, or let us say present in T but not present in T star. This has to be there. We know T is not equal to T star. These are two different trees. This means there must be at least one edge E in T which is not present in T star. Then only they can be different trees. If all the edges are same, then both these are same trees. Let us assume that this edge E is the first uncommon edge that is present in T. So if you follow the Kruskal's algorithm and you are building the tree T, let us assume the first edge that is not present in T star, that is what we are calling as E. Okay. In this case, if that E exists, then adding this edge E to T star, this will form a cycle. Why is it? Why is it that if I add this edge E to T star, it will form a cycle? The reason is T star, you know, is already a minimum spanning tree. If you add one edge to any spanning tree, if you add one edge, it will form a cycle. This is the property of spanning tree, and we had discussed it in detail in spanning tree lecture in data structures lecture series. So according to this property, if you are adding any edge to a spanning tree, it is guaranteed to form a cycle. So because of this, if you add this edge E to T star, it will form a cycle. What I'll do is, let us say your tree is something like this. Let us say this is your graph. Something like this is your graph. And we'll take a spanning tree from this. If I remove this edge and this edge, this is a spanning tree. Let us say I added this edge E and formed a cycle. So this need not be the actual full spanning tree. I'm just taking that part which is forming a cycle. So let us say A, B, C, D, E. And here I have an edge called E, and this edge is newly added into T star. So I'm just assuming that this is the portion of T star which is forming a cycle. See, I'm drawing this just for illustration purpose. Actual T star can be whatever. I'm just drawing a cycle and I want to illustrate and show you how this cycle is formed and how the future developments on this happen. Okay. So we are as of now assuming that because you added E to T star, it formed a cycle, and let us say this is the cycle that is formed. Okay. If this is true, then listen this carefully. This is the most important part of this proof. If this is possible, then there must exist another edge called F, which is part of T star but is not part of T. Why is this possible? Why is this right? It is correct because if this edge F is not present, that is such an edge which is part of T star, which is part of this cycle but not part of T. If this sort of an edge is not present, then T will always contain a cycle. Why is it? Because this is a cycle and I am saying F is one edge in that cycle which is not present in T but is only present in T star. If this F is not possible, that means all the edges that are present in this cycle are present in T, which means T must be having a cycle. But we know that T is a spanning tree, and because it is a spanning tree, T cannot have a cycle. Because T cannot have a cycle, there must exist an edge F which is part of this cycle, which is part of T star, but is not present in T. So at this point, you know, there are two edges which are part of this cycle. One is E and the other is F, and E is part of T and F is part of T star. My next point is, if this situation exists, then the weight of edge E, this must always be less than or equal to weight of edge F. Do you know why this is right? This has to be right because Kruskal's algorithm adds edges in non-decreasing order of weights. This is the rule that we follow in Kruskal's algorithm. Whenever you want to add an edge, you will always add the smallest edge first. That is, you are adding in non-decreasing order of weights. Because of this, if F is an edge with smaller weight than E, Kruskal's algorithm would have picked F before E. Here, F is not part of T because Kruskal's algorithm preferred E over F. That is why T is what you formed using Kruskal's algorithm. T star is your true MST. So, whatever is formed from Kruskal's algorithm, you preferred E over F because E is having a smaller weight than F. That is the only possibility because Kruskal's algorithm picks edges in the order of their weights. Because of that, we are sure that weight of E has to be less than or equal to weight of F. At this point, we have two possibilities. One is that weight of E is less than weight of F, and the other possibility is that weight of E is equal to weight of F. Let us consider both these possibilities. First case is weight of E is lesser than weight of F. If this is the case, then replacing F with E in T star would yield a new spanning tree, let us call it T dash, with a strictly smaller total weight than T star. Just think about it, why this is right. I'm telling you that if it is the case that weight of E is less than weight of F, then replacing the edge F with edge E in T star. You know E is not present in T star, but F is present in T star. And what is our claim? We assume that T star is the true MST of this graph. If this is the case and you replace this edge f in T star with edge E, that is if I remove f and I put E, then I'm telling you that this will give you a new MST which is having strictly smaller weight than T star, and let me call it as T dash. This new MST T dash, this is having strictly smaller weight than T star, which means T star cannot be the MST. What is MST? MST means minimum spanning tree. That is, it should be having the minimum sum of edge weights among all the spanning trees. But when we assumed that T is what you got from Kruskal's algorithm, but that is not the MST, but there is some other MST which is T star, then we'll ultimately reach this conclusion that another MST called T dash is possible, which is having an even smaller weight than T star. If that is the case, then this refutes the fact that T star is an MST. Because if you know another MST which is having even smaller sum of edge weights, that means that is the MST. T star cannot be the MST. So because of this, our initial assumption that T star is the MST which is having maximum number of edges in common with T, that assumption is wrong. That is, in case weight of E is less than weight of F. Let us consider the other case as well. That is, what if weight of E is equal to weight of F? In the case when weight of E, if this is equal to weight of F. If this happens, then what is the scenario? If this is the scenario, here if you do the same thing, if you replace the face F, that is the edge F, with edge E in the MST T star, this time it is not going to yield a spanning tree which is having lesser weight than T star. So this thing is not a problem. T star will still hold as the MST, but the problem this time is, this time even though T dash, which is the new MST that you are forming by replacing F with E, even though it is having the same weight as T star, there is another problem. The problem is T dash is now having one more edge in common with T than whatever T star is having. Why is it? Because E is an edge which is present in T. And you know E is not present in T star. And what did we do? We substituted F with E, which means you added an edge which is present in T and you removed an edge which is not present in T, which means this new MST called T dash that you formed by replacing F and adding E is having one more edge in common to T than what T star was having, which means T star is not the MST which is having maximum number of edges in common with T. So this again contradicts the assumption that we made that T star is the MST, the true MST, which is having maximum number of edges in common with T, which means whatever was our initial assumption, that was wrong. What was our initial assumption? Our initial assumption was that T, which is the tree that we formed from Kruskal's algorithm, is not the actual MST and it is just a spanning tree. This assumption was wrong. Because of that, we reached contradictory points at the end of this proof. So what is our final conclusion? The final conclusion is that because both our assumptions came out to be wrong, our initial assumption has to be wrong. So what was our initial assumption? Our initial assumption was that T, which is formed from Kruskal's algorithm, is not a minimum spanning tree. If this assumption is wrong, then what is the correct statement? The correct statement is that whatever you obtain from Kruskal's algorithm, the tree T, that itself is the minimum spanning tree. So this is the proof for the fact that Kruskal's algorithm always produces minimum spanning tree.